Hello everyone, my name is Habib Rehman. I'm a PhD student at King Mongkut University of Technology, Thonburi. The title of my presentation is Iterative Algorithms for Solving Variational Inequalities and Fixed Point Problems. And the main objective of this study is to construct new iterative methods to solve variational inequalities involving quasi-monotone operators in infinite-dimensional Hilbert spaces. The main advantage of the proposed iterative method is that they are use monotone and non-monotone variable step size rule based on a mapping information rather than its Stitches constant or other line search methods. And the outline of my presentation, the short introduction of variation inequality problems, some lemmas and identities, algorithms to solve variational inequalities, new algorithm to solve variational inequalities and fixed-point problem, some more algorithm to solve equilibrium and fixed-point problems. Throughout the presentation, we have the following notions: C to be closed convex set of a Hilbert space, subset, inner product and norm, real numbers, natural numbers, and operator is denoted with A. Variational inequality problem, shortly we write VIP and we denote strong convergence and weak convergence respectively. A short introduction of variational inequality problems. A variational inequality problem for an operator A is defined in the following way. Find x star such that A of x star y minus x star is greater than equal to 0 for all y in C. It is important to note that variational inequality problem is equivalent to solve the following fixed point problem defined like this way. It is a projection and rho is any positive real number. Next we have a definition of operator monotonicity. A mapping is said to be strongly monotone for some constant, some positive constant if for every xy this inequality holds. Strictly monotone if this inequality is strictly greater than 0. Monotone if this inequality is strictly greater than or equal to 0 for every x, y, and c. We have pseudo-monotone. If this inequality hold implies that this inequality hold for all x, y, and c. And then we have a quasi-monotone, which quasi-monotone is a bigger class and it contains all previous monotonicity definitions. Variational inequality theory is an important tool in economics, engineering, mechanics, mathematical programming, transportation, and others. The projection methods and its variant forms represent important tools for finding the approximate solution of variational inequality problems. The first projection method proposed in 1966 by Pollack, it's called Pollack projection method. It's starting with any x0, then we iterate for the next iteration by using the projection of this quantity, and alpha is a step size which depends upon the Lipschitz constant and strongly pseudo-monotone constant, and PC denote the projection. In 1976, Korpelevich proposed an extra gradient method, which is also called two-step extra gradient method, and it used to solve monotone variation inequality problem. And in the first step, we start with x0, then we get yk, then we get xk plus 1, which is next iteration, and alpha is a step size. which depends upon the Lipschitz constant. And we can and extra gradient method can be graphically described like this way. We can start with x0 or xk, and this is the xk minus alpha ax. Then we can project on c and we get yk. In the next step, we use yk instead of xk, and then again project on c and we get the next iteration xk plus 1. To improve the previous method, in 2011, Sensor introduced a new simple method which is called the subgradient exagradient method. It is also two-step exagradient method. The first projection on C and the second projection on a half space. Uh, Rather than C, this is not C, it is denoted by metric projection. And the graphical explanation of the subgradient method, we start with xk, compute xk minus alpha axk, then project on C, and then we use yk and the projection on a half space rather than on a C. Some inertial algorithm. Now we introduce the concept of some inertial algorithm. We have the derivative of a function by using Taylor theorem, forward difference, backward difference, central difference for the second derivatives. The discretization is the name given to the process that we use to convert a continuous equation into a form that can be used to calculate some numerical solution. For example, Stepen descent method can be seen as a discretization of the first order differential equation, which is defined like this way. To accelerate the convergence rate of the algorithm, in 1964, Pollack considered the second order dynamical system, which is defined like this way, and using the discretization process, he converted the numerical procedure to calculate the solution of the above differential equation in the following sense, which further can be written in the equation number 4, in the form of equation number 4. The iteration is called intra-exploration algorithm or the heavy ball method. The term xkx minus 1 is called momentum, and the term beta xkx is called extrapolation point, and beta is called extrapolation factor. Important lemmas and identities. This section will recall some important lemmas and identities. We know what is the metric projection is defined like this way, and these are the properties of metric projection. We have two important identities which are useful to prove the strong convergence of a sequence. We have this lemma for to prove the strong convergence of a sequence. There is one more lemma which also helps to prove the strong convergence of a sequence. For any sequence, then there is a subsequence to satisfy this condition, and then there is a non-decreasing sequence mk such that this inequality holds. These two lemmas are also useful to prove the strong convergence of a sequence. There are two sequences. One sequence satisfies this condition, and if we have this, then second sequence uh, satisfies this condition. Similarly, there is another result which is useful to prove convergence of a sequence. A new algorithm to solve variational inequalities. There are two algorithms in this section to solve variational inequalities, and the operator is a quasi-monotone. The algorithm 1 It uses non-monotone subgradient hexagradient method. We start with step 0 with initial 1 point. Lambda 1 is step size, mu is any fixed number, and then there is a 5k sequence who satisfies this condition. We choose another sequence alpha k who satisfies this condition, and beta k satisfies the following conditions. The step 1 is the first projection by calculate by using xk and lambda k. If xk is equal to yk, then stop, otherwise go to step 2. In step 2, first we construct a half space by using the sensor idea, and then compute the second projection on a half space. And the step 3 is a Mann type step size which used to prove the strong convergence of a sequence. And in step 4, we update the step size by using this formula, and we add phi of k sequence which help to produce a non-monotone step size rule. The algorithm 2 is the inertial method, which is the extension of previous method. Uh, we choose for inertial, we choose two starting points, rho, mu, and lambda 1 uh, work like this way, and beta k satisfies this condition. First, we compute inertial step, and inertial step defined like this way. We add this term beta k plus xk rho of k and this term, which this term helps to prove the strong convergence, and rho of k is defined like this way, and epsilon k is dependent on beta of k. In step 1, we project on C and obtain yk by using wk. In the second step, we construct a half space and then project on a half space and get the next iteration. And finally, we update the step size rule by using this formula, which is also a non-monotone step size rule. For this step size rule, we need to prove that this is bounded below and convergent to some points. That's why we have this lemma to prove that this step size is bounded by this interval, and we can easily prove by using Lipschitz continuous property. By using mathematical induction and by exposing these two terms, and by definition of lambda k, we can add this term, and this is convergent series by using equation 9. Similarly, we have to need to prove that this is to prove the convergence of this series. Let's we suppose that this is not convergent, and then we can show by contradictory way that this is not possible in equation 10. So due to the convergence of both, in 10 we have obtained lambda k approaches to lambda. This completes the, so this is gives the guarantee that this series is bounded and convergent. Okay, new algorithm to solve variational inequalities and fixed point problems. First, we define a bitter constructive, demi-constructive mapping, which is defined like this way. And secondly, we take a beta and a sequence in 0, 1 such that to satisfy this condition for some a greater than 0, and this beta is a demi-constructive constant. Algorithm 3 is inertial method to solve fixed point problems. Uh, in step 0, we choose inertial points and inertial control parameters, initial control parameters by taking this one. In the step 1, compute inertial algorithm and inertial factor update by equation 11. In the step 1, we compute the projection. In step 2, we construct a half space and then compute a projection on a half space. And then step 4, we calculate a fixed point, which is like a Mann iteration. And then we update the step size in step 5. In the second algorithm, we use the Sung extra gradient method to solve fixed point problem instead of two-step extra gradient method. And the step 0 is the same as the in previous one. In step 1, we compute the inertial step and inertial factor updated by equation 30. In step 1, we compute this for first projection. In step 2, this is not a projection. This is a simple, which is more computationally. It is easy to compute this step rather than a projection. In step 4, we compute a Mann iterative scheme to calculate the fixed point problem, and then we update the step size rule with a different method, and this step size rule is monotone, which is not non-monotone. Next, we have equilibrium algorithm to solve equilibrium and fixed point problem. This is the inertial method to solve fixed point problem and equilibrium problem. With step 0, we start with step 0 by choosing two initial points and then other control condition for the algorithm. In the first step, we compute inertial step, which is defined like this way, which help to prove the strong convergence. And this second term help to prove the strong convergence. In step 1, we calculate y of k, which is a minimization problem, which is used to solve equilibrium problem. If wkyk is equal to, then we stop, otherwise we go to the next step. And then in step 2, we calculate lambda k f of yk by using y of k. In the step 4, we calculate the fixed point problem by using Mann iteration, and in the steps 5, we revise the step size by using this formula, which is also a monotone. Thank you for listening. These are my contact information. Thank you very much.